Hi everyone. In today's lesson, we're going to talk about how to solve limits algebraically using something called direct substitution. So the steps for solving limits algebraically will always be to try direct substitution first. If your answer is a real number, meaning a whole number, a fraction, or a decimal, then that is your final answer. So normally, you'll have an example like 1, 2, 3, and 4 without the picture. I just want to show you what the answer is graphically so that we can prove it algebraically as if the graph was not there. So the first question is asking us to find the limit as x approaches pi of sine of 2x. So here's the graph of sine of 2x. So since there's no plus or minus, that means I'm asking you for the limit as a whole. So I need to check both the left and the right side. So here's pi. So the limit from the left and then the limit from the right looks like the y value that this graph is approaching is in fact 0. So we know the answer is 0. Let's prove it algebraically. So the way direct substitution works is plain and simple. You directly substitute the value that you have. So sine of 2x, but instead of x, we're going to put pi. So sine of 2 pi is what we need to find out. Now you should be thinking unit circle, and that 2 pi is 360 degrees. So if you have your unit circle, I care specifically about this point over here, which is the point 1, 0. And we know that sine is the y value at 360 degrees, which is in fact 0. So without the graph, we know that the limit is 0. All right, let's try example number 2. So I want to find the limit as x approaches 3 of this quadratic. So obviously, if we have the graph, we can go to where x is equal to 3, and we can approach the graph from the left and from the right, and we can see that it's approaching the y value of -2. Both the left and the right are equal. So let's prove algebraically that we will get that same value. So the way that direct substitution works is that you plug the number directly into the equation. So -2, 3 squared, plus 16 times 3 minus 32. So take a minute, pause the video, and type this into the calculator just the way you see it, and hit resume when you're ready for the answer. All right, so you should have gotten -2, which is what we had when we looked at it graphically. Perfect. All right, let's try example number 3. All right, so number 3 is saying find the limit as x approaches -4. Well, if you look at your graph of the function, x equals -4 is here, and it doesn't look like this curve is actually on a specific whole number. So we're probably going to get some sort of decimal. But maybe we could figure out what it's close to be, right? So as x approaches -4 from the left and from the right, it looks like it's a number that's going to be less than 1. So let's prove it and see what that number actually is. So why don't you guys try direct substitution, pause the video, and then hit resume when you're ready for the answer. All right, this is what I got. So when I did it, I actually did the top separate and then the bottom separate, and then I divided them. You could probably have plugged this all into the calculator in one shot, and you should be getting 0.2, which is exactly in between 0 and 1. All right, why don't you try number 4, pause the video, and then hit resume when you're ready for the answer. Okay, here's the answer. So if you look on your graph, it's somewhere in between -2 and 4. I plugged in 3 for x, and I got the square root of 5, or negative the square root of 5, which is approximately -2.236, which is in fact between -2 and -3. All right, that is kind of it for direct substitution, and I'd like to move on now to piecewise functions. All right, so if we remember correctly from piecewise functions, we either have a smooth connection or a jump or a hole connection. So what do I mean by that? So let's just say I have a piece of a quadratic that, looks something like this, where there's an open circle and then the quadratic goes to the right of the graph. But then I have a piece of a line, and that line has a closed circle at exactly the spot where the parabola had an open circle, and the line goes down this way. So what you would say at this specific spot where the parabola and the line meet, that there's a smooth connection there, This is actually called a continuous function, which we're going to talk about a little bit later on. But this smooth connection tells us that the limit from the left side of the graph and the limit from the right side of the graph will approach the same y value. So if we know that there's this smooth connection, the limit will actually exist because the limit from the left equals the limit from the right, which is that specific y value. Now, you could have a jump or a hole connection. So let's just talk about a hole connection. Similarly to the smooth connection, let's just say we had that quadratic that connects, but now this time the line that connects doesn't fill in this circle. How does that affect the limit? Well, the limit from the right and the limit from the left looks like they're still approaching that same y value. So it's okay if the hole is filled in or not, that limit will still be the same. So the limit from the left and the limit from the right will actually exist because they are equal. Now, what if I had a jump connection? So again, let's try the same picture. Let's just say I have our parabola going up like such, and let's just say my line doesn't start until down here. So if I wanted to find the limit from the right and then the limit from the left, theoretically, this would be a different y value. So this would be a y value, which we'll call y value A. And then this would be a different y value. We could call this y value B. So in this scenario, the limit from the left is actually not equal to the limit from the right. Therefore, the limit will not exist. So these are the types of scenarios that you're possibly going to have when you have piecewise functions. So the only way to determine if the left and the right side are equal, or if the left and the right side are not equal, is we actually have to test both sides using direct substitution. So if we take a look at this, it says evaluate each limit using direct substitution. So I apologize, this seemed to have formatted a little bit funny. So technically this one's going to go over here. We want to find the limit as x approaches 5 of f of x. So in problem number 1, they're asking you to find the limit as x approaches 0 of f of x. So f of x is this piecewise function here, and we want to know what's happening at 0. So notice we have this piece of the graph when we're less than 0, and this piece of the graph when we're between 0 and 4. We need to decide, are they meeting at the same spot or not? So we have to check the limit from the left and the limit from the right. So you want to think of a number line, right? And we want to break it up into 3 pieces. We have 0, 4, and greater than 4. So we're going to be using this graph for when x is less than 0. So that's this side of the graph. Then we're going to be using this square root function when x is between 0 and 4. And then we're going to use this rational function x over 4 when x is greater than 4. So these are the 3 parts to your graph. The colors should help. So if I want to see what's happening at 0, I need to check the left side and the right side. And theoretically, this is your left of 0, and this is your right of 0. So you have to check into this equation and this equation. So let's do that with direct substitution. So we're going to check the left side of the graph. So the left side is this one, 1/2 x squared. So 1/2 0 squared. Well, we know 1/2 times 0 is 0. And then let's check the right side of the graph. Well, the right side at 0 is this green one, which is the square root of x. So at 0, we'll plug in the square root of 0, which is 0. Now, since the limit from the left equals the limit from the right, that means it must connect. It doesn't have to connect and be a hole, right? We could have 2 different scenarios. It could connect with the hole on top of the open circle, or it could connect with just a hole. It won't matter. So they connect, therefore, the limit exists and the limit is 0. All right. Now I would like to find the limit as x approaches 4. So now if we're talking about x equals 4, we have to consider this scenario over here. So this is the left side of the graph now, and this is the right side of the graph. So I can cross this out, and I can say here's my right side of the graph, right of 4, and here's left of 4. So the left side of the graph, I'm going to use the green, which is the square root of x. So I'm going to plug in square root of 4, which is 2. And the right side of the graph, I'm going to need to use the blue, which is the rational function. So the square root, so 4 over 4, which is 1. So the limit from the left does not equal the limit from the right. That means there must be a jump here, some sort of jump in my piecewise function. Therefore, the limit does not exist. So the scenario that you see here is actually this one. We have one other y value and a separate y value, therefore it's not the same. And last but not least is the limit as x approaches 5. So if you notice, 5 is somewhere over here. 5 is not on an endpoint where one graph begins and the other ends, right? 5 is all in here. So 5 is an x value that's greater than or equal to 4. So all we would have to do is plug it into this bottom function. No need to plug in left or right. It's not in an endpoint. So all we're going to do is do 5 over 4, which will be your answer of your y value. So 1 and 1/4, which is 1.25. And that is your final answer. All right, that's it for today. If you have any questions, now is a good time to jot them down, and we'll see you in class tomorrow. Have a good night.